Welcome back. In video 3, I'm going to discuss molar heat capacity, which is a similar concept, but just a little bit different. So in specific heat, we talked about the energy it takes to raise 1 gram of a substance by 1 degree Celsius. Now we're dealing with the amount of energy it takes to raise 1 mole of the substance by 1 degree. So you can imagine it's going to be a much bigger number. It's going to take a lot less heat to raise 1 gram versus 1 mole by a degree Celsius. So let's just dive in. Conceptually, really similar, like I said, to the previous problems that we've done. This version of the problem, I'm given my number of moles. Notice that my equation is only slightly different. I have an N here instead of an M, so I have number of moles instead of mass. Still have heat, still have specific heat, still have change in temperature. We're still going to use Celsius, so nothing major changes there. Looks like I've got moles and I've got C, so those are good to plug in as is. But I definitely need to figure out my delta T. Just like we did before, we'll go delta T equals temperature final minus temperature initial. So delta T is going to be 51 degrees Celsius minus 23 degrees Celsius. So delta T, let me make sure I didn't leave off any decimal points. No, I didn't. Is 28 degrees Celsius. So there's our delta T. Now we can just kind of plug and chug. Q equals 1.55 moles. C, 75.38 joules per mole degree Celsius. And our delta T is 28 degrees Celsius. That's in parentheses. Okay, so something I want to point out before I solve the problem. Notice how much bigger our molar heat capacity is. That should pass the smell test. That should make sense. Really big specific heat, really big heat capacity compared to the specific heat. The other thing that I wanted to point out is we should have expected to see this in the unit, right? It's per mole, it's not per gram, so we should have expected to see a number of moles. So moles cancel, degrees Celsius cancel. So I'm left in joules. That's a measurement of Q, so that's good. So for this one, I get Q to be 3271.49 joules. Again, that's bigger than 1,000. Don't love it. Let's convert it to kilojoules. 3.27 kilojoules is our answer. I just divided by 1,000. The first video in this series shows this conversion. This is a 1 to 1,000 ratio. So if you need to look back at that, please do. If you need help, come see me, and I can help you with that one. So this is kind of version 1 of a molar heat capacity problem where you're given temperatures and number of moles, and you're asked to calculate the amount of heat that's required to make this change. Let's look at a second problem type. Okay, so here I've got my given listed. I didn't list my need because I wanted to give us a little bit of space to finish that last problem. Clear up some room here. My need is N. So this time I'm solving for my number of moles. I've got the other information. I got to solve for N. So I'm just going to got ahead of myself a second. Notice I went ahead and solved this for the N. That's what's tripping up a lot of us with our math. We're struggling with algebra more than we're struggling with chemistry. So let's make the algebra easier. Let's solve for N ahead of time, and then we're just plugging and chugging. So let me step over to the other side again. Okay, so I've got my 1450 joules over 25 point, I think that says 35 joules per mole degrees Celsius. And I got to multiply by my delta T. Ooh, they gave me my delta T this time, so I don't have to calculate it. That saved me a step, so that's good. And that equals N. So if I look at my units, cancel degrees Celsius because it's on bottom and on top. I can cancel joules because it's on top and on bottom. My moles is on the bottom of a compound fraction, so that unit comes up top. When I do the math on this one, I get 2.54 moles equals N. So fairly straightforward math problem here. Once we get solved for our n, the math is really easy. Now, I keep saying it's really easy, but I think we're struggling with this math a little bit. So to solve this, let's take a step down here. To solve this, I need to take 1450 joules. I need to multiply these two things together. So if I multiply 25.35 times 22.5, that gives me 570.375, and my unit would be nothing. Yeah, because joule moles moved up here, joules canceled. So I would have this setup. So if you're having trouble, if you're consistently getting incorrect answers when you have these fractional problems, go the long way. Show the multiplication here in your denominator and then do the division, and that should give you 2.54 moles as N. So same answer. Okay, so that's style 2. Style 3. Notice the big difference here. I'm given a number of grams, and I'm dealing with molar heat capacity, so I'm going to have to go grams to moles. Somehow, some way, I got to get grams to moles. Luckily, I've known how to do that for months. I've got temperature initial, temperature final, going to have to change those to a delta T, and I got my C. Luckily, I don't have to do anything there. Remember, if I'm going grams to moles, I find this number on the periodic table. I find the molar mass of sodium, the molar mass of chlorine, add those two together, that gives me my molar mass of sodium chloride. The grams have to go on the bottom because they're on top here, and I need to cancel them. Okay, so that's 58.44. Didn't want to have to add it up in front of you as I'm talking. So I've got grams sodium chloride on top, I've got grams sodium chloride on bottom, I'm into moles of sodium chloride, and that works out to be 0.40 moles NaCl. So that'll be N. I started my delta T math up top. I just kind of laid out the equation and gave myself kind of a framework. So my final is 21.7 degrees Celsius. And my initial is 56.8 degrees Celsius. So my delta T is going to be negative 35.1 degrees Celsius. So we got to be really careful with signs when we're dealing with heat, because you'll see at the end the question doesn't care about the sign. It'll make more sense at the end. So just know that if you see a negative sign for the next couple of weeks, pay attention to it. It means something special. So I've now got a delta T, I've got my N, I've got my C, I got everything I need to calculate Q. So let me plug it in. Q, N is 0.40 moles. My C is right here, so I've got 50 joules per mole degrees Celsius. And my delta T was negative 35.1 degrees Celsius. Before we get lost in the math, unit cancel. Moles on top, moles on bottom. Celsius on top, Celsius on bottom. Left with joules. Q is measured in joules, so I'm good there. Just multiply across. My Q works out to be negative 702 joules. Now here's where the sign manifests itself. If you look at the question doesn't ask what is Q. The question asks how much heat is leaving the system. This does not answer that question. The answer to the question is 702 joules of heat are leaving the system. The negative sign tells you that it's leaving. If it's a positive sign, that means the energy of the system is increasing. So we're talking about endo and exothermics. That's going to be a whole nother topic. We're going to have to spend some time looking at what it means to be endothermic and what it means to be exothermic. For right now, this negative sign tells us that we're losing heat. It's more of a direction than it is a sign. So the negative means we're losing heat. If we get a positive Q, we're gaining heat. So I hope those make sense. I gave you 3 different versions to look at. Hopefully this helps with practice problems and things like that. Please come see me if any of this didn't make sense or if you need clarification.